Hi everyone, welcome back to my math YouTube channel. So guys, today I want to talk about this type 3. We have already covered two types to evaluate the integrals of rational functions and using the partial fraction decomposition method. So guys, let us look at this type 3. In type T, again, in all these three types, we're going to have rational functions. So if I have a rational function of the form, we have p of x, and then that is in the numerator, and in the denominator, in this case, we have something in which is also thought of as irreducible quadratic functions. So let us say I have functions like this: a1 x squared plus b1 x plus c1, which is a standard quadratic form, and then I have like n of these times a2 x squared plus b2 x plus c2, and it just keeps on going. Let's say we have the last term here is an x squared plus bnx plus cn. Okay, so if I have a rational function of this form, so what is unique about this guy is that the denominator, which I usually like to call as q of x, the denominator is an irreducible quadratic function. So guys, that is very important to note here. The denominator is irreducible quadratic form. In the previous cases, if you have already watched my videos on type 1 and type 2, the denominator could be factored, and type 1 you could get like distinct factors, linear factors for the denominator. In type 2, we may get repeated factors, right? But they were still linear. Guys, in this case, we have quadratic factors, and when it says they are irreducible, that means we cannot find or write the factors for them. Okay, so that is something that we have to keep in mind before we start actually evaluating the integral of a rational function. First, we have to look at the denominator and see what type of factors can it be factored or not. So guys, that is one of the conditions, and the other condition, which is this two other conditions. So the other one is, guys, I'm going to write them right here. The first one is that the degree of the numerator. So we are still consistent with what we actually said in type 1 and type 2, that is the degree of the numerator. So degree of the numerator, in this case the degree of the polynomial function in the numerator, has to be less than the degree of the denominator. So it's strictly less than the degree of the denominator. Okay, that is the first condition. Well, this is consistent with the other types as well. And then the other one is that the factors downstairs, as you can see right here as well in this general form, of course they are irreducible quadratic it is the irreducible quadratic form, but they are all distinct factors. We cannot write factors for each individual piece by itself, but what you see right here are still, you can all still think of them as factors, but they're all supposed to be distinct, which you can already see right here. Okay, so it has to satisfy these two conditions. If it satisfies these two conditions, then we can write this ratio as in partial decompositions as partial fractions. So this can be written as, so guys, be careful, this is slightly different. This can be written as a linear function, not just a constant. It's a linear function. So a1 x plus b1 divided by the a1 x squared plus b1 x plus c1. That is the first piece, and then plus the second piece will be a2 x plus b2 divided by the second one here, which is a2 x squared plus b2 x plus c2, and then it will keep on going, and the last one would be an x plus b. And guys, keep in mind, this is the general form. When we actually look at the examples, we are not going to be dealing with n number of terms in the denominator. It would be probably 2 or 3. So the denominator is going to be, in this case for the last term, is an x squared plus bnx plus cn. So this is how we write the partial fractions for a ratio which looks like this. The degree of the numerator is still less than the degree of the denominator, and the denominator, you can see our irreducible quadratic form is in the irreducible quadratic form, but with n, in this case, distinct factors, okay? And guys, if you see on the right hand side, I mean the partial fractions, again, it is slightly different than the other types, type 1 and type 2. We don't only have a constant upstairs, we have a linear function of the form mx plus b, a1x plus b1, then a2 plus x plus b2, so on and so forth, right? So this is the type 3. Guys, please take notes on this. I mean, I'm sure if you are doing calculus, you have this in your textbook as well. I would still like you guys to think about why it works this way. I'm not really trying, I mean, I'm not telling you exactly why it's working. All we're saying here is like, this is what we can write as a formula. So I'm going to use it in my next video to show you or to illustrate like how we can use this to actually evaluate the integral for a rational function, okay? So guys, take notes on this, and I will see you in the next video with an example where we will actually use this partial fraction decomposition. Okay, till then guys, take care. I will see you in the next video.